All right, good afternoon, everyone. How's everyone doing? Yeah? Chilling? Cool. All right, so this is lecture number 4. So some quick announcements. As usual, we have our live lectures here on Piazza. There's also going to be a code sample that I'm going to be working with in a bit, so if you want to fire that up and download it, you can kind of follow along that way. You can also answer, or you can ask questions that we can answer on that Piazza as well, if we can't get to that here. Midterm 1 grades are out, and so if you want to submit a regrade request, make sure you do that by Friday. There are some guidelines on that release post on how you should format your regrade request, so make sure you read that thoroughly and make sure you follow that format to hopefully communicate your ideas more clearly, so that when we review it, we can make sure that we're giving a very fair look at it again. Okay. Project 2 Gitlet is out, as you're aware, and it's due on the 26th. So everything you need to do the project you've already learned, right? So this is like a software engineering project. It's not like there are more concepts to go. So if you just want to sit down with your partner and just try to knock it out, you can absolutely do that. So you already know everything you need to know to do it. Also, there are going to be a couple project work days, so kind of similar to what we have on Monday, except not design reviews, but there's just a space for you to work on the projects, and those are on calendars. And typically that's going to be on Fridays, but don't forget there are still quizzes on Friday, so even if you don't plan to stay for the entire project workday, make sure you still show up on time and take your quiz. Okay? Also, one more thing. So we've been saying that labs are due 22 hours after the start of your section. So those deadlines are now enforced on GradeScope. We reran all the submissions, so if your submission was a little late, maybe you want to double check it to see if you still have those points. And if you don't, you can reactivate an older submission to try to get some points back. Slip days and other extensions aren't accounted for yet, so if you use a slip day, or if you had an extension on assignment, we haven't put that into the system yet, so for now, I'll say it's late. But if you know you have it, just keep an eye on it, and hopefully later, the score will go back up. Okay? Okay. So let's get on with it. Let's talk about tree traversals. All right. So that was last Thursday. So first of all, we learned about recursive traversals. So you can use recursion in order to touch every node in the tree, right? And the pseudocode looks something like this. So you had binary tree traversal function that takes in a node, and right off the bat, you can pre-order process it, right? And to process a node means to just do something to it, right? So you can print the node, you can square the node, you could do something like that, okay? And then recursively, you want to try to repeat this procedure on the left side if it exists. So if there's a left node, then make a recursive call on the left. After you make that recursive call on the left, then you can process it here instead. And if you process it here, then that's called in-order processing. Okay. And then after you in-order process, you can see if there's a write. And if there's a write, you can make a recursive call on the right side. And then afterwards, if you want to process at that point, then that would be called a post-order processing. Okay. And so this is a little diagram. You saw this in lab. So if you have a tree that looks something like this yellow line represents the order in which we visit the nodes using our recursive calls. And then the red pegs indicates when we're going to actually process them, right? And so for pre-order, if you put this red peg on the west side of every single node, then when the yellow line runs into the red peg, that is the pre-order processing of it, right? And this is a really fast way in which you can come up with the order when you're doing this on an exam, right? And we also learned in the lab that if you want to do in order instead, you just put the peg on the south side of every single node. And if you want to do post order, you put it on the east side of every single node. And this always works because it matches up exactly with its pseudocode, right? Because this yellow curve is the order in which we're making the recursive calls. And so whenever the yellow line touches the side of a node, that's when we have access to it in this function call. Right? And then if we put the peg on, say, the west side here, then basically the first chance this yellow line skims a node, it's going to be printed, right? Which is why it aligns with pre-order. If we want to do it between the left and right-hand side calls and we put it on the south side, then that's in order because that's between the left recursive call and the right recursive call. Right? So that's why this trick works. Okay, we also learned about iterative traversals, right? So we know that if you want to do something over and over again, you either do it recursively or iteratively, right? So to do it iteratively, you have pseudocode like this. So you create a fringe. A fringe is just a data structure that's just holding nodes that you're trying to remember, right? And then you're, of course, going to put your root into the fringe to start it off. And then while the fringe is not empty, you're going to pull that off. And then you're going to add its children. And then you're going to process the node you just pulled off. Okay, so that's the pseudocode for iterative traversals. And if you use a stack as your fringe, then that will result in DFS, which is depth first search traversal, right? And then if you would use a queue for your fringe, that would be breadth first search traversal, right? And you can remember a stack is like a stack of pancakes. So if I'm cooking a bunch of pancakes in the diner, the first pancake that comes off of my grill top and onto my plate is the last one to be eaten by the customer, because you have to eat them top to bottom. Or you could try to eat the whole stack at once if they're super hungry. And then for queue, right, a queue is just like a normal line. So if you're setting in line for fish and chips, or you hear people are setting in line for coffee or something like that, then the first person that shows up to the counter is the first one to actually get their drink or get their fish and chips, right? So it's like a stack of a queue in normal line. Okay. So we've also learned in lab that it turns out that iterative DFS is basically the same as recursive preorder. You get the same order of letters that come out, right? And so let's kind of take a closer look as to why that is, right? So let's look at this top box here. So this was the pseudocode for the recursive traversal. So let's only focus on preorder right now. And so here I've made a diagram that shows like what our recursive stack looks like. Okay, so when we first start this recursive code, we're going to start with node A, right? So we're going to call binary tree traversal on node A. And the first thing that happens is we're going to preorder print it. So I've indicated that by just bolding the A and making it red. Okay, so A gets preorder printed, and then it checks the left, and if it's not null, it's going to make a recursive call there. So the left of A is not null, it's a B, and so I'm going to make a new function call using binary tree traversal on B now, right? And so if you think about like the visualizer, right, like you have a function call for B that's active now, but the function call for A is still, like it's still waiting to be completed after B is completed, right? So this is what your function call stack looks like, okay? And then when we get to B, so when we're evaluating the function call for B, it's going to be preorder printed right off the bat, and so that's why B is bolded, right? So it's going to be printed, and then it doesn't have a left and it doesn't have a right, so nothing else happens to B, right? So that function call ends, and B can leave our recursive stack, right? That frame is closed, that function frame is closed, so it goes away, and we return back to evaluating A's function call, right? And so where did we leave off with A's function call? We left off over here after we made the recursive call on the left, which was the B, right? So we're going to continue on this line right here, okay? And so at this point, we're going to look to see if the right is null. It's not null, it's a C. So now we're going to make a recursive call on C, which is why C appears in the stack, right? A is not done yet, so that function frame is still open, but now we have to evaluate C's function call first, and so on and so forth. And so that's, if you follow that logic, this is kind of what all the recursive call stacks look like. Okay, similarly, if we kind of trace through this code for the iterative pseudocode, then we're going to start with the A. We're going to add that to our fringe, which, because we're doing DFS, we're using a stack, right? So we're going to put A into the fringe down here, and we're going to, while the fringe is not empty, so it's not empty because there's an A here, right? We're going to remove the next from the fringe, which is the A. So at this point, the fringe is empty, but we're holding on to the node A, right? And then we're going to add its children to the fringe, so that's B and C. So B and C get added into the fringe, so we have B on top and C under it, right? But A is already gone, it's out of the fringe, and then we can print A, right? So that's why A is bolded down there, okay? And then we go back to the top of the while loop. So is the fringe empty? No, it's not, there's B and C in it, right? So we're gonna remove the next from the fringe, which is B, okay? We're gonna add its children to the fringe, it has no children, so nothing needs to be done, and then we're gonna process that remove node, so we're gonna print that B, okay? So after that iteration, our stack looks like this. We only have C, right? And we can kind of continue like this, right? But if you notice, like, so I've highlighted the stacks in which stuff is printed, right? And so you can see that they kind of match up a little bit, right? So like there's a stack here where A is printed, and that's because like A is on top at this time, right? B is on top at this time, C is on top at this time, D is on top at this time, D is on top at this time, right? There's some extra stuff like floating around down here, like there's an extra A here and there's an extra AC here. But it doesn't matter for pre-order because like at this point in time, like the CA stack right here, it doesn't matter that A is under it, like it's nice, right? But for pre-order, we don't need it because A is already been printed like the first thing, right? So it doesn't matter that A is missing on the bottom one, like we can still successfully do a pre-order traversal, right? But this is problematic if we wanted to do like an in-order or post-order traversal, right? Because in this bottom situation, like A is already gone from the beginning, right? And now it makes sense why, like, if we're doing this recursively, like we can print A here or here or here or here, like A is kind of always available to us, right? But if we're doing this iteratively, A is gone, and so we can't really do anything with that. Okay. So that's kind of why like this iterative traversal method is like naturally pre-order. Like when we use the pseudocode, it's going to be pre-order, right? But we can try to modify this in order to allow us to do in order or post order, right? So today we're going to try to do in order instead. So let's take a quick look at in order. So if you kind of follow this code, like I won't walk through this again, but the main idea is that like you can see that between this slide and the previous slide, like the top row of stacks is exactly the same, but just the time in which stuff is printed is different, right? So basically, like we can take advantage at different times and print at different times instead, but all the stacks are going to look exactly the same. But we note that like with this iterative stack, like there's no way this pseudocode can allow us to do this because like if we're going to print B first here and then we're going to try to print A later, like A is already gone. Like we can't print A after B, right? So we have to try to modify this code a little bit. Okay, I have a big red X because we can't do that. Okay, so how can we change this code so that we can do in-order traversal? So this takes a little bit of like scratching your head, and you might have to like fiddle with this a little bit. But let's try to take a look at this. So we want a state like this. We want B on top of A because A needs to be printed after that, right? So in this case, A is important. A needs to be here. So maybe when we start out with this tree, like let's add A to the stack and then let's add B right on top of it after, right? Because we need to have this BA state here. Okay, and then after we do that, then let's see. So B can be removed and then A is by itself. And then can A be removed or should C go in on top of it before it's removed? Well, in order traversal, it goes B, A, and then C is later, right? So probably at that point we have BA and then we have A, and then A needs to leave before C goes in, right? Because if A is stuck under C, then we're in trouble, right? So we have BA and then we have A, and then, okay, so now we need to deal with C, but before C comes out, D needs to go in, right? So it looks like we're going to start at the root, we're going to add its left and maybe all the other lefts after it, and then when it comes out, we're going to step over to the right and add its left and all those lefts. And then after that's all done, we're going to step right and add that after it. Okay. So this is kind of what the pseudocode looks like. And of course, like this is kind of like a logical jump. You would have to fiddle around with this and maybe try some different examples to kind of get this idea down, right? But this is something that looks like it'll work. So basically, we can start here at this root, and we add that into the fringe, but we also add the root's left into the fringe. And if it had a left, we'll add its left into the fringe. So we'll add all these lefts into the fringe, right? So that will give us our BA stack that we were looking for, right? And now that we have BA, we can process B and we can remove it. And now we have A that's exposed, right? And so A can be removed. And remember, A needs to leave before we put in other stuff. So A can come out. And then we're going to add A's right and also its left and its left and its left and its left, right? So now we can have C in there and then it's left D on top of it, right? D has no children, so that's fine. So D can come out. And once D comes out, then it's time to print C before we go on to its right and add E, right? So this is kind of like the general pseudocode that we want to work with. Okay. All right. Does this make sense to people? Are there any questions on how this pseudocode is going to work? Okay, cool. Let's implement this. Before we implement this, let's write some tests. All right. So tests are very useful because, like, we have a guess that this algorithm will probably work, but maybe we messed up somewhere in our logic. So if we have tests, then we will know for sure whether it works or not. So here are some tests. So this one is just a null node, right? So a tree with just a null node, that's a good test to have. Another good test to have is this, where we have just a root, right? So just a single root as our binary tree. Okay, here's another one. So we can have one that goes left and left, and we can have one that goes right and right. Okay? We can have one that goes left and then right, and then one that goes right and then left. Right? So you're just kind of like coming up with all these different scenarios, like, you know, like I want to try to flesh out anywhere where my algorithm is a little fishy, right? So here's one where it's like left, and then there's like left and right. And then here's one where it's just like a bunch of stuff, right? So hopefully if my algorithm has all these trees, I'm like reasonably confident that either one, my algorithm works, or two, I must have missed something. But I think this is kind of comprehensive. Maybe you can think of a little more to add. Okay? But this is a good place to start. Okay, so with that, let's implement this. Oh, one more thing. Okay, so we think this algorithm will work. Let's make this a little more challenging because I think we can. Let's try to use constant space instead of linear space. So you're given the tree, and like that tree is going to take linear space to hold all those nodes. But maybe I want to do this traversal using constant additional space rather than linear additional space, right? So linear additional space is what we've been doing. We have a whole stack structure, or we have this whole recursive tree structure, and I have to open as many frames as nodes I have potentially, right? So that's like a linear amount of additional space. But I think we can do this in-order traversal using a constant amount of space, right? Why are we doing this? Well, I don't know, but I had this as an interview question once, so this is kind of interesting to figure out. So let's try to do this with constant space. I think it's very similar because, for instance, if I told you like we are sitting on node C, what is the next node that should come after that in order? E. Yes, E, right? Because like if I'm at C, like I have to go to E, like that's the next one in order, right? So like if I'm at B, what's next, right? It has to be A, right? So it's like no matter where you're sitting, you have to know like where you're going to next. So we can write logic to figure this out. It's not like, you know, it's not like we're at C, maybe we're going to A, maybe we're going to B. Like no, we're like definitely going to E for in-order traversal, right? Okay, so let's try to do this in constant space. I think the only difference is that like, so here we have BA, so maybe like we go all the way left first, right, to sit on B. And then like once we're done with B, we're gonna go to its parent, right? And same thing here, so we go to A, and then after that, remember we're going right and then left, right? So we go down to D, but then once we're done with D, we're gonna go up to its parent, to C, and then we're gonna go right and left, and so on and so forth, right? So I think the only difference is that, you know, we're gonna go, instead of going like right, left, 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 add those alt and fringe, like we're just gonna go down there, and then when we wanna go back up, we'll just go to its parent, right? Okay, so let's implement that. So here's like a binary tree class, okay? This is all there is. There's a root node, and then I have a node class that's nested in it that has a left, right, and I'm gonna add its parent. We haven't had a parent in lab, but if I put a parent, then that will allow me to go back up, right? Okay, so now our goal is to fill in the in-order method. And of course, I've taken all of those test cases that we saw on the slide, and I put them into a tester file, and they're named according to the color they were on the slide, so it doesn't matter, there's like just a bunch of them, right? And I've just kind of filled them in, and I built the trees in kind of like a hacky way, but at least these are all the trees, and they're represented in code, basically, okay? So if you want to follow along, you can. I put this code on the Piazza thread. Okay, so first let's kind of make sure that we did the test cases right. So let's implement this based on the way that we know. Let's try to do this recursively, right? So let's do an in-order recursive traversal. So I'm going to implement this up on the screen. If you have it out, why don't you try to do this? It's exactly the same way we did it in lab, all right? Okay, so first thing I did was I made a helper function, right? Because according to the pseudocode, which is here, right? Like I need to have a node parameter, but I didn't have that, right? And so if I want to keep track of extra information, I need to make a helper function in order to keep track of that. And then next, I basically just copy this pseudocode. Okay, cool. So this is basically exactly the pseudocode. If there's left, go left, then print in order, and then if there's a right, go right. Okay. So let's run the test and see if it works. It says I have a null pointer exception. Uh-oh. So this failed on red, which was this. Oh, this was the case in which I had just a tree with a null root. So why would this cause a null pointer exception? Oh, here, right? So I clicked on this line, it brought me here, and then I called helper on null, and then I go here and I say, oh, okay, so null.left is a null pointer exception because I can't do that. So maybe I need to have a check here that says, like, if the root is null, don't do anything. Okay, cool. Let's try it again. Oh, if root is not null, then do this. Okay. Aha. So now I printed all of them in a row. So I think I need just a new line when I'm done with this, just so that it prints each test on a different line. Oop. Aha. Okay. Cool. So these are all the in-order traversals. Forgot to mention this, but we were clever with our tests because these are not only binary trees, these are binary search trees, right? And so if you remember from lab, that means like the left of all these is smaller and the right is bigger in every situation, right? And so if you do an in-order traversal of a binary search tree, you should get all of the numbers in order, right? So that's why our tests are so pretty, and we can like easily tell whether we're right or not because all of these are putting them in ascending order. Cool. So we know that our tests are put together properly. Let's try to do the challenge that we had now. So let's try to implement this using constant space and iteratively. Okay. So how would we do this? Well, okay, maybe let's delete this. Maybe I should have made a git commit before I deleted all this, but let's try to do this iteratively. So maybe, okay, so if root is null, let's just stop. Let's just return. Otherwise, let's do our iterative traversal. Yeah, question?
How much space does the recursive in order use?
Right, so recursive in order also uses linear space because, like, if you think about asymptotics, right, like when you make recursive calls, you're still analyzing the recursive tree, right? And so if you're drawing that many recursive calls, like that's still linear space. Yeah. Okay. So let's see. So I need to know what node I'm currently sitting on. So let's define a pointer for that. Okay, so I'm starting at the root, but remember, we don't want to start at the root. We want to go all the way down to the left because that's the first node to be printed, right? So I need to go all the way left. So how can I do that? Well, basically, I can say, well, if the roots.left is not null, the cur is now the left, right? And I can keep doing that until I hit the bottom, the leftmost node. Okay. Okay, cool. So now, at this point, I'm starting on the leftmost node, which should be the first one. Okay, so now, what I want to do is I want to print that node, and then I want to move to the next one, right? And I want to do this until I'm done, so probably until cur is equal to null. Okay, so there's two situations, right? So looking at these trees, we said that we wanted to, so if I'm sitting down here, then if there's a right to it, I want to go to the right and then go all the way left, right? So for example, this purple one, the leftmost node is actually the 0, right? So this is the one I would start on. But the next one is the 1, right? So I want to go right and then all the way down to the left as my next one because 1 comes after 0, right? So that's if a right child exists of our current. We want to go right and then all the way left. If we're in this green case, then basically, if there's no right child, we want to just go up to the parent because that is the next node. Okay. Okay, so I just typed up what we just explained, right? So if there is a right child, so if it's not equal to null, I'm going to go right, and then I'm going to use the same loop as before to keep going left until I can't go left anymore, right? So that is the first situation. If there is no right child, then instead I'm just going to go up to the parent, okay? And that is it, right? So let us run this algorithm and see what happens. Okay, this is taking a while actually. That is strange. Oh, ooh. Okay, so any guesses as to what's happening? We have an infinite loop somewhere. Right? Okay, so how can we figure this out? Okay, where is this coming from? So if you use the debugger, you can put a breakpoint here at the top of the test, and we can see which line is responsible for this. Okay, so is it here? So this button here is step into, so this will evaluate the call, and this button here is step over, so I will just proceed down on the screen and run one line at a time. So let me hit this button and see if it works. Okay, so the red one is fine. Okay, the yellow one's fine. Green one's fine. Oh, okay, the blue one is the one that's causing the problems, right? Because it's still spinning right now. So something's wrong with the blue. Okay. So let us go figure that out. So basically, what is going on? We can put a breakpoint here, and we can use the step into button instead, and we can look and see what's going on. Oh, so this is creating the tree, so I don't care about this. So let's go back up, and let's go down again so we can actually evaluate the in order. Okay, so let's see. Is this fine? That's fine. That's fine. That's fine. That's fine. What is going on? Let's open up the Java visualizer. What is going on? So it's really clear what's going on now, right? Basically, we're running the same block of code over and over again, right? And we're switching between the 1 and the 2. And so actually, it turns out there's a small bug, and the bug is that it depends whether you are a left child or a right child. Because here, we're down at the 2, and we should be done. But what is it doing? It's going up to its current, so it's going back to the 1. And of course, the 1 is going to go back to the 2, right? So if you're a right child, you should actually not go up to the parent. You should keep going up until you are no longer a right child, and then go up one more. All right, so you might have to think about that a little bit, but we're running short on time, so let me just fix that. So if you are a left child, you're good, just go up. If you are a right child, then keep going up until you're no longer a right child and you're a left child now, and then go up one more. Okay, so what did I type here? So I said that, well, first of all, this thing here is just to prevent a null pointer exception on the next condition. So the next condition is the important one. So if I go up to the parent and then I go back down to the right, if that's equal to the cur, then that means I'm a right child. Yeah. if my cur.parent.right is equal to me, that means I am a right child of my parent. Okay, so if that's true, then I'm going to go up. All right, and I'm going to keep going up until I'm a left child, and then when I'm a left child, that's when this condition quits, and I'll run cur equals cur.parent. If I'm a left child in the first place, then this while condition won't run, and I'll just go up. Okay. Let's run this, stop and rerun. Voila, so we have all these, and they all look good. All right. Cool. Let me move on to one more quick thing. So iterators, we're going to learn about iterators tomorrow, so this is just a very fast preview. Okay? So what is an iterator? An iterator allows us to do like an enhanced for loop. So you've probably seen something like this, like you can do for and then string s for all the stuff in my string array list, and you can do the syntax. But how can I do the syntax with the class that I've defined, right? So in order to do this, I need to implement the iterable interface. So if you look at the Java API, the array list implements iterable. Okay? So as long as I have something implement iterable, I can do this enhanced for loop syntax on it. Okay. And so if you look at the API, actually iterable requires a function called iterator. Well, where the heck am I going to get an iterator from? Well, I need to make another class that implements iterator. So that's why there's iterable and iterator. So this is kind of like comparator and comparable, right? So the important difference, how do you remember this? Like iterable is like an adjective, so it's like it's like an adjective, right? It's like my data structure can be iterated over, right? It's iterable, right? Whereas iterator is like a mechanism. Like this is the thing that dispenses like my next item, right? So if you think about like, you know, those like red things at those deli counters, right? Like that thing is an iterator because it's dispensing tickets, right? Whereas the ticket wheel inside, that like the roll of tickets, that's actually iterable because it's like the roll of tickets and you can get like one thing at a time from it, right? Okay. So yes, so let me really quickly convert this into iterable and iterator. Okay. So I want to make my binary tree iterable. So all I can do is I can say implements iterable. Okay, and immediately IntelliJ is yelling at me because I have not implemented the required methods, so I can do option enter. I can do option enter, implement methods, okay. So now it's saying I need to fill this in. Well, I need an iterator of integers, but I don't have one, so I need to make one. Okay, and then we see that an iterator requires two things, has, next, and next. So basically what I can do is I can take this code and move it into here, right? So, well, node cur is like what I'm keeping track of, so I can have this inside of this class here. Okay, right, and so when I ask for the next, then I'm supposed to dispense like the next cur. I'm supposed to move this forward. So instead of having like this while loop that loops through everything and prints things one at a time, like I'm going to feed it through next instead. So what I can do is I can take all of this logic here, and I can move this inside of the next function. Okay. And if you remember from before, what we were doing was we were printing right off the bat before we did anything, but instead we want to return this number, right? So we can save it at the top, and then we can return it when the function is over. Okay, so that looks good. What else did we have? Oh, we had this if root equals null thing. Is that important? Well, basically, there's this other function you have to fill in called has next, right? So basically, it's supposed to return true if there's more to dispense, or false if there's nothing to dispense. And so we can basically say if cur is null, we should not dispense anything. Anything else left to do? Oh, remember the first thing we did was we didn't start at the root, actually. We started on the leftmost thing, right? And so we can't just start this iterator on the root. We have to start it on the leftmost thing, and you can do that inside a constructor. So let's move this initialization into a constructor instead. Okay, so now we're ready to test it, right? So everything is set up now. So basically, you can test it like this, right? So we have to make an iterator, and then we're going to check if there's a next. If there's a next, then we can print out the next item. And we keep doing that until there's no more nexts. Okay, so I made an iterator, and I'm using the orange tree that I had before, which just returns a binary tree, and I'm calling the dot iterator function, which is this thing over here. Oh, it returns null right now, so I need to return a new my iterator. Yeah. Okay, and so now, while that iterator has next, I will print out the next. What happened? Why is nothing printing? Let us use the debugger. Oh, so the while loop doesn't go in. That's funny. Why doesn't the while loop go in? No current, correct root. Okay, no one correct, but what? Yeah, that's the bug. Okay. Ta-da! Okay, there we go, we got it. So basically, we made this transformation. We just kind of moved our while loop code into an iterator. And the iterator is like the deli meat red thingy where it dispenses those tickets so that you can get help, right? So you pull a ticket out of it, and you check if there's a next. If there's next, you can pull another ticket out of it, right? So that's kind of what an iterator is, and we'll do that tomorrow. Okay, so let us move on to the next portion of this section.
Hello? Okay. Good job to Matt for finding those bugs. It's really stressful being up here and trying to find a bug, so good job. All right, so now that we've finished talking about iterables and iterators and all this stuff, I just wanted to recap what went through lab for the past few days. So like the tree stuff, especially the balanced search tree stuff and the RedBlack tree things. So this next part of the lecture is just going over what we've talked about already, and then Jackson's going to talk about what you're going to do tomorrow, like more of that. Alright, so just a trees overview. Remember that through the past few labs that we've noticed that BSTs have potential performance issues if they get really spindly. Right? That means they have that really long chain down there, and it ends up being more like a list rather than the tree that we want to benefit from. So the worst case for binary search trees is when we insert things in sorted order. Right? Then that whole tail is going to be forming on that right-hand side. And the main issue is that we were super lazy with where we placed all the elements. Like we didn't care where we put them, we just said greater things go on the right, smaller things go on the left. And we didn't care about where we put them, which resulted in this kind of behavior. So one solution, maybe we can insert in random order, because if we do it randomly, maybe that'll help us get a better distribution. Why don't we just do this? There is just one problem, is that we might not have our data all at once. Right? Maybe someone's giving you this data as we go. We don't always have all the numbers that we want at the very beginning, so this won't work for us. The way that we address this problem is through overstuffing the nodes to a certain extent. Right? So the tree, we want to make sure that they can never get imbalanced, so we just put a bunch of numbers in a single node and hope that works. Right? So that's the general idea of what we want to do, is that if we have a node, or if we have a tree like this one, and we want to add the number 13, we'll just stuff it into this bottom node here. We're not going to add any more leaf nodes, and we're just going to put things in nodes that already exist. Right, so this is not actually what happens, but this is a general idea of what we want to achieve with what is called B trees. Right, so B trees, we talked about this, I believe, yesterday in lab with like 2-3 and 2-3-4 trees, but B trees is just a special word for a tree that can have more than one item per node. All right, so more than one item per node means that you can have more than just 2 children. So the most popular types of B trees are ones with really small order and ones with very, very large order. And when we talk about order, we're just referring to the amount of children that a certain node can have. All right, so small order B trees are what we saw in lab yesterday, and those are the 2-3 trees and the 2-3-4 trees. They're usually just conceptual, like helping you better understand how to store data. So these are more conceptual, but in industry and in many other applications, they will be using very, very large order trees, such as nodes with thousands of children. And this is mostly used in databases and file systems, so like those types of applications. I'm not going to go into that too much, but if you're interested, you can take the CS 186 course here, which is a databases class. It's really cool, and they actually make you implement a B tree there. And it's a lot of work, so you'll see, it'll be fun. So definitely recommend if you're looking into databases or anything like that. Okay, so yeah, order is just the maximum number of children that a single node can have. There's things with small order and things with very large order. Okay, so the trees that we'll be concerned with for the rest of this lecture will be the 2-3 tree. So a 2-3 tree is a type of B tree, and it has order 3, which means that there is at most 3 children, and that's where the name 2-3 actually comes from, is that 2-3 is referencing how many children a single node can have. It's between 2 to 3. All right, so because each node can have between 2 to 3 children, that means that each node can have 1 to 2 entries. All right, so just keep that in mind. Even though it's called a 2-3 tree, that's referring to the number of children it can hold rather than the number of items that it can hold. All right, so 2-3 trees, they can have 1 to 2 items, but 2 to 3 children. And every single node must have one more child than its entries. So if you have 1 item, then you have 2 children. If you have 2 items, then you have 3 children. Okay, so we never really know what B tree means. Like, we don't know if B means balanced, or if B means bushy, or B means broad. So this is just a quote from some guy who really likes B trees, so feel free to read it on your own time. But yeah, the most important methods that we care about for B trees are the get and insert methods. So you did probably a lot of this in lab yesterday, but remember when we get any kind of key that we're looking for, it's the same procedure as if we were doing a binary search tree. We look at a node, figure out if our item is there. If it's not, we'll go to the correct child where the number should be. The only difference is that in this tree, there's more than just 2 children. There's, in addition to the left and the right, there's actually like a middle child. And if there's a 2-3-4 tree, you'd have 2 middle children. So it's the same procedure that you're used to. Check if the number compared to the items that you have, see if it's there, and then go to the correct child depending on where that item should be. All right, so let's say we wanted to get 3 with this tree that we have right here. We would start at the top and say, is 3 in this node? We would decide that there is no 3 in this node, and we would figure out where to go from here. Because there's a 20 and a 40, we know that 3 is less than 20, so we'll go down this side of the tree and explore 10 and 18. We'll do the same thing and explore this side of the tree with the 1 and the 3, and we'll end up finding the 3 over there. So it's very similar to what you've seen before with binary search trees. There's just more checks that you have to do for a single node, and you have more decisions to make whether you want to go left, middle, or to the right. Okay, so I think I didn't explicitly mention this, but items in the middle will just have values in between these 2 keys. So note that the search property still exists. Things to the left of a node are less, things to the right are greater, and things in the middle are in between. Okay, and then here is just the other operation that we're more concerned with, which is the add. It's the same procedure really as a binary search tree where we would go down to the leaf and add it there, but the only difference is that leaves can get too full. Right? We don't want a leaf to have like 1,000 items in it, because then that ends up becoming effectively a list again. So we want to make sure that each of the nodes have between 1 to 2 items in it. So we'll have to do some splitting to make sure that that is the case. So let's walk through this in a little bit. We have the same tree that we had before, and we're trying to insert 8 into this tree. So the first step is to walk down the tree like we're doing get k, and we want to just find the leaf that we want to insert into. So we'll start here, go down, and now we've reached the leaf. Okay, so the next one is Now that we've reached the leaf, we want to add the key to the place it should be. So we reach the leaf node, we'll add the item in here. The 8 will go at the end of the one with 3. And now we need to make sure that the nodes aren't too full. Right? So this is the next step. If the resulting leaf node has 3 entries, that's too much, right? They can only have between 1 to 2 entries. We'll split the node by sending the middle element up and then rearranging the rest of the tree as it should be. So for this one, this node has too many items. Let's split the node, and that will consist of taking the middle element, which is the 3, pushing that up, and then rearranging what the tree should look like. So it'll look like this in the end. All right, so the 3 was originally over here. We popped it up to the top, and we had the 1 and the 8 are now split from each other. Okay, so we're going to keep repeating this until we'll repeat this if this creates more problems for us. So we notice that there's another problem here. There's too many items. So we're going to repeat this process, push that 10 up, split up the 3 and the 18, and we're going to do it one more time until we have a completely balanced tree. Okay? Did anyone have any questions about those 2 procedures that we did? All right, perfect. So now our tree is completely balanced. So just as an observation, just note that 2-3 trees will have perfect balance. This is not a technical term or anything, but just you can tell that these trees are going to be a lot more balanced than the regular binary search trees that we saw. So just note that when we split the root, every node gets pushed down by exactly 1 level. When we split a leaf, the height doesn't change. So the only time that our tree can get taller is if our root ends up getting split. All right? So that's what keeps our trees really short, is that the only time that our tree can gain height is through splitting the root, and that will take us a really long time to get the root to split. So just note that we will never get unbalanced trees that look like this. Based on how this insertion process works, we will never end up with a tree that has this one child C that's living at the bottom right here. Because remember, if our tree was without the C and we tried to add it, it would be pushed up rather than pulled down. So I don't have too much time to explain why we won't get trees like this, but I really suggest you just try to add some numbers to a tree and figure out if you can get something that looks really spindly, because through the insertion process of 2-3 trees, you actually won't end up getting anything that looks like this tree over here, which is imbalanced, and this tree over here, which is also imbalanced. Okay, so just to quickly talk about runtimes, because we mentioned that these trees are perfectly balanced, they're not going to be spindly, the height will be between log base 3 of n and log base 2 of n. And the bases, don't worry too much about those, but that's if the entire tree has all 3 children or all 2 children. But just note that it'll be in between log n, it'll have that height. So all the operations that we end up doing, like get and insert, they will both take, in the worst case, log n time, which is pretty good. These are the runtimes that we want to shoot for. So just to explain a little bit, get, you have to traverse down the entire tree to find the item in the worst case, and that would take log n because we know our tree is at that height. And insert, we'd have to do the same operation, traverse down the tree, add it to that leaf node, and in the worst case, every single one of the things along the path, the nodes along the path will have to be split, but that will only be log n splits that we'll have to do in the worst case as well. So get will be log n, insert will also be log n, so they're both pretty good. All right, so before we talk about problems with this, does anyone have any questions about runtimes or anything we talked about B trees? No? Okay, so feel free to put your questions on the live lecture thread as well. We'll be happy to answer any other questions that you have there. Let's start talking about the problems. Oh, yeah.
Do you mind just going over the insert runtime one time?
Yeah, so the question was, can we go over the insert runtime? I did go over this a little bit fast, so thank you for reminding me. But remember, when we insert, we go down to the leaf, insert it there, and then we have to make sure that no problems arose by splitting all the way up. Right. So in the worst case, we'd have to go down to the bottom to insert into the leaf node. So let me go back to this over here. So we'd have to walk down the tree. That would take log n time with respect to the height, because we have to go all the way down to the bottom. So this is the log n operation right over here. When we add the key, it doesn't really take too long to do that, but the other log n factor comes in from trying to do the splitting. So if this one has to do a split, that takes 1. This one has to do a split, we'll have to do another. If this one has to do a split, we'll have to do it again. So in the worst case, every single level we went down, we'll have to split as we're coming back up. Does that help a little bit?
Yeah, so it's just like 2 log n.
Basically, yeah, it's going to be like 2 times the height or 2 log n. Any other questions? All right, perfect. So now let's talk about the problem. So these runtimes are really good, but the problem with 2-3 trees is that they're actually really hard to implement, especially the remove operation. So if you take 186, you're going to have a great time implementing these B trees, but it's really hard. It's really tough to implement this. So unfortunately, beautiful algorithms are not always the most useful, so we'll have to come up with a different way to do this. So what tree did we use to fix this problem? Yeah. Right, we use left-leaning RedBlack trees. So we'll talk a bit about what those are. So there's hope. We can use what we call RedBlack trees to help us more easily implement this idea of 2-3-4 trees and 2-3 trees. Generally, just note that RedBlack trees are binary search trees. Keep that in mind that they are binary search trees, and they just color nodes red and black to help us, the programmer, remember how to organize things and how things are organized. So just note that red, this means that the node is in the same B tree node as its parent, and black means it's just like any regular node. And we'll see what this all means once we go into an example. But just note that RedBlack trees, they have a correspondence with 2-3-4 trees, but left-leaning RedBlack trees have the 1-to-1 correspondence with 2-3 trees. And we'll talk a little bit, we'll be talking about left-leaning RedBlack trees for the rest of this lecture, but just note that there are those 2 types, RedBlack trees and left-leaning RedBlack trees, and we'll see why one has a constraint and one doesn't. Okay, so like we were saying, we have these left-leaning RedBlack trees. The RedBlack tree used to implement these 2-3 trees are what we call left-leaning RedBlack trees. Remember, I want to really ingrain this into your heads that these are just normal BSTs. Just remember, they're normal BSTs, except we just color the nodes kind of weird. There is that 1-to-1 correspondence between the LLRB and the 2-3 tree. And the red doesn't mean that the node acts any differently. It's this convenient fiction that we say, but they don't do anything special. They just tell us, and they give us more information about how this tree is going to be organized. All right, so they don't do anything special, but they're mostly a note for us to know that red means that these 2 nodes are connected together. So like I was saying on the other slide, red means that the node is in the same B tree node as its parent. We can see that in this example right over here. So if this node is red, this one is black, that means this 10 is in the same B tree node as its parent, and we have that representation right over here. All right? So just remember that this gray box, it doesn't actually exist, but it's basically what this is telling us, that if something is red, that means it's in the same node as its parent in the B tree. So this 10 and 18, they're linked together. So the representation in the 2-3 tree will look something like this. Okay? Yeah?
Does the 1-to-1 correspondence just mean it's only like 1, 2, 3, 2 every that's left here?
Exactly. So the comment was, what does the 1-to-1 correspondence mean? And that just means that the 2-3 tree, there is exactly one left-leaning RedBlack tree that is equal to it. There's not any other representation in it. Mm-hmm. Okay, so the question is like, why don't we choose right-leaning? Because if we have a node with 2 entries, they can actually be represented left-leaning and right-leaning. They could be represented in both these 2 ways. We will just be choosing the left-leaning as a convention. We don't really have any better reason than just like, let's always go left, because it helps us as a programmer be more organized where we can find these left nodes. We could have picked right, but for our case, and I think the person who invented it also picked the left-hand side as well, so we'll go with left, but just note that the 2 nodes actually have 2 representations, which is why 2-3-4 trees have not a 1-to-1 correspondence. It's because of this. Okay, so I just wanted to give you some time to practice drawing a RedBlack tree, so I'll give you around 1 minute to do this, but draw the left-leaning RedBlack tree that corresponds to this 2-3 tree. If you don't have a pencil and paper, just try to draw it in your minds, but it's really important to know how to do this conversion because this is also a very common test question. So practice this. I'll give you guys like about a minute and then we'll check back in with you in a bit. Okay, so I hope you guys have at least gotten a shot to just try drawing some of this out. We'll just have to move forward just in the interest of time, but what this red-black tree, or what this 2-3 tree will look like in a left-leaning form will be this one right over here. So maybe you'll ask, like, how did we get this here? But one way that you can approach doing this is just figuring out, at this node, what should the left-leaning red-black tree look like for this particular node? We know that we have a 10 and a 17. We want things to be left-leaning, so we know that this 10 and 17 will look like this 10 and 17. And then with this 1 and 5, we have the same representation with the 1 and the 5. 19, 21, we have the same one here. And the 13 goes right in the middle. So this is actually similar to what you did with the build red-black tree method in lab yesterday. It's kind of just like doing that, but on paper instead. So just make sure you know how to get this and just practice. We have a few past exams you can also practice this on with some random trees. So I think this is a really good skill to know. Okay, so just like another random thought, remember that this is a BST as well. It's a binary search tree. So searching in the left-leaning red-black tree for a key is the same way that you would do in a BST. Right? This tree, even though it's colored kind of weird, it's still a binary search tree at heart. So any kind of insertion that you do, any kind of contains that you do, you'll go through a similar process where you would check the root, figure out where to go from there, and repeat that process over and over. So searching in this red-black tree is actually pretty easy because it's exactly like a BST. Okay, so the next question is like, how do we construct these? In lab, we did ask you to do the build red-black tree method, but just note that introduces a lot more complexity than you actually need because you'd have to create the B tree first. B trees are hard to implement. Then you'd have to convert that to a red-black tree, which is really annoying too. So why do we have this conversion? Why can't we just insert into it directly? So that's what this next section is going to be talking about, is that we're going to talk about how the insertion works, right? So that's one of the other methods that you had to do yesterday, but we will do this insertion as follows. So just remember, regular BST, LLRBs are just a regular BST, and we will insert actually as usual into a BST, but the caveat is that after we do that insertion, we're going to do 0 or more rotations and color flipping to maintain that one-to-one mapping. Right, so this is pretty vague right now, but we'll break down every single case together and then we'll see how that insertion will actually happen. All right, but just note that this insertion process, you're inserting like a regular BST, then you're fixing any problems that it created. Okay, so that's what we're going to do, and we'll dive in just right now, but does anyone have any questions before we get into the details of inserting? Yeah. Okay, any other questions? All right, perfect. So I want to get through as much of this as possible, so hopefully this will make sense, but please, please, please stop me if anything is confusing or if anything that I missed. This stuff is really confusing, so just let me know if there's something that I can re-explain. But yeah, I'm repeating a lot of stuff in this lecture because I really want you to know that there is this one-to-one mapping, and this one-to-one mapping is what is going to drive this insert method. So remember, one-to-one mapping between a 2-3 tree and a left-leaning red-black tree, and the implementation of a left-leaning red-black tree is actually focused on maintaining this one-to-one correspondence. So when you're performing any LLRB operation, just think about that you're inserting it into the 2-3 tree and what we would do there. And then figure out what the colors would do, what the colors would mean, like if something is being added to this node, what color does that mean this node has to be? All right, and we'll dig into every single case to see exactly what color it has to be. Okay, so we're going to now talk about the cases. I want to explain how these slides are going to work. So what's going to happen is that there's this LLRB world, and then there's this 2-3 world down here. So we have this 2-3 tree world in the bottom, which means this is the operation that we're trying to do in the 2-3 tree world. What will it look like in the LLRB world? So this is why this is so important that there's this one-to-one mapping, is because the colors that you choose, the rotations that you do, the flipping that you do, is focused on making sure that this 2-3 tree is exactly the same as the RB tree that you end up making. Okay? So let's say that we had S in our 2-3 world, we added E to it. So what color should we use when we're adding this E? So we know that when we have an S, we're trying to add an E. Because this is still a BST, we're putting that E on the left. But what color should this E be? Red or black? Does anyone want to help me out? You can just shout it out. What color? Red. Yeah, so this color should be red. Always use red because remember, when something is red, that means you're in the same BST or same B tree node as your parent. So saying that the E is red means that you're creating this node here. So if we had this SE with the E being black, we wouldn't have this picture right here because that's not what two black nodes connected to each other means. What this means is that we have a black node at the top with the red node connected to it, which means that they are in the same B tree node together. Right? Does that make sense? Does anyone have questions about that? Okay. So just remember, every time we insert something, it'll always be red at first. Anytime we put in a node, when we get down to the bottom of the tree, we have to color it red. Okay? All right, next thing is, let's say that we have this tree in the 2-3 world, and we're trying to add S. Right? S would go to the right of this E. And this is our left-leaning RedBlack tree. Suppose that we have this this leaf E, and we try to insert this S. Remember, S would go to the right of the E because we're using a BST. So let's add this red S to the right. All right, are we good? Is there any problems with this? Yeah, does someone want to help me out here? What is the problem here? Just raise your hand. I'm calling on you. Yeah. Exactly, it is not left-leaning. So what do we do to help fix this? Rotate, yeah. So here we have a problem because this is, oh God. Okay, sorry, the mic almost died for a second, but we have a problem here because it's not left-leaning. So this red is on the right. The way that we fix this is through rotation. So we're rotating this SE, we're rotating the E, and notice that this doesn't change the 2-3 representation. It's only changing our LLRB representation. So if we ever have something that is added on the right, and it's a red node, we'll have to do a rotation to fix that. Okay? So this is just us trying to maintain this one-to-one correspondence here, because if we were given a left-leaning red-black tree that looked like this, we would have no idea what to do with it, because we don't understand red nodes on the right. We only understand red nodes on the left, which is why we need to do this rotation. Okay? All right, so the next thing is, we're going to talk about another insertion, but just note that if we ever have these 4 nodes that get created, 4 nodes mean that there are 4 children possible, we want to represent them in this way. All right, so just trust me on this one. There's not really any good reason for why we want to do this yet, but if we ever want to represent something with 3 items and 4 children, we want to represent it in this way. This is the state that we want to get to. And we'll figure out why this is the case in a little bit, but just this is what we're trying to aim for. So we want to have this, if there's any time that there's 3 children, we want it to be 1 red or 1 black with 2 red children. Okay, so what happens if we have this case? So we have B, A, S, Z in the 2-3 world. We're trying to add an E to it, so the E would go on the left. this is our left-leaning red-black tree representation. And if we try adding this E to the left, we'd get something like this, right? We'd follow the same BSC insertion, figure out that it goes to the left here, and mark it red. There's a problem, right? So this is not the 4-node representation that we were looking for before. So what is the thing that we should do to fix this? Rotate. Yeah, so once again, the problem is fixed through this rotation operation. So we have these two red nodes linked together. This doesn't make sense in our 4-node representation that we talked about before. So we need to do rotate Z, the rotate Z operation, which will bring the S to the top and get us into this formation here. All right, so now we're in this case that we wanted to be in. All right, does that make sense? Does anyone have questions about that? Good so far? Okay, cool. So like we were now in this state, but we still have a problem, right? We don't have that 2-3 node invariant that's being held here because we have a node that has 3 children and we have a node that has 3 items, instead of 2 or 1 item. So now we need to figure out how to fix this part. Okay. So we have this representation here. We've kind of just switched trees into a cleaner example, but we have the same problem at hand, that we have this 2-3 tree with the A, B, C, which is in one single node, which means there is too many items in this one node. All right, we want to get this B to be pushed up. We want the B to be connected to G, and the A and the C to be split apart from each other. Right? This is a split operation that we were talking about. So does anyone have any idea of what we should do here? What is the operation that helps us transform ourselves from this one tree on the left to the one that's on the right? Yeah. Yeah, we will change the colors. So this is the color flip or flip color method that you were doing yesterday. This is what it's doing. So we will flip the colors. We'll end up with B being red and B's immediate children flipping colors to black. So you might ask, why does this actually help us? Because nothing about the tree actually changed, but it's the coloring of the nodes that has changed, which means something to the program, right? Because when we change this color of B from black to red, you're saying that B is now connected to the parent in a way that they're in the same B tree node, right? B is now connected to the parent, so that's these two nodes being together, which is the same representation that we wanted here. And the A and the C, they're now not associated with the B directly, they're not in the same node, and they're each black nodes because they're separate in this representation as well. So no rotations happen, no I don't know what other things you can possibly do to do this, but nothing about the structure changed, right? It's only the coloring that changed, but this means a lot to us because us as a programmer knows how to deal with the colors, and having the colors being in this way tells us that this tree is now in the correct formation, right? So B, it's a left child of the G, and we have A and C separate from each other, which is this representation that we want, okay? All right, any questions about that one? That one's a little bit tough, so anyone have any questions? Okay, cool. So that's actually it. So all that stuff, all that spec in the lab, it's really just trying to describe this procedure. Remember, when we're inserting into a red-black tree, always insert with it being red. Then ask yourself these 3 questions and say, okay, if it's a right-leaning node, we'll rotate it to the left. We'll rotate it to the left. If there are 2 consecutive left links that we saw before, we'll rotate it to the right. Then if there's any 4 node, which is the one with 2 red children, we'll do a color flip there. All right, so these are just the 3 cases. There probably seems like there's a lot of different possibilities, but it actually breaks down to these 3 cases chained together. So this is the insert method. There's a lot of small details, but hopefully that helps kind of clarify why the rotations and color flipping actually helps us create this 2-3 tree. All right, so just one last detail is that we have a possibility of cascading operations. So if we had one color flip that maybe messed up that section of the tree, we'd have to fix it, and maybe it would create more problems higher and higher. So we'd have to make sure that we fix any cascading issues. So let's just go through a quick example of some cascading example over here. So let's say that we have this 2 through tree, B, A, B, S, and then we add Z to it. All right, so adding Z to it, we'd actually end up getting this tree over here. Right, so when we added Z to it, get this tree, we want to make sure that we flip the colors. We flip the colors here, which would in turn mean that we're splitting the ESZ node. Right, so we want to split ESZ, that translates into color flipping, so we'll end up getting this tree over here. Right, does anyone follow that so far? We got to this tree at the end. Is there any problem with this tree? Is everything left-leaning in this tree? No. So we actually have this S that's living on the right-hand side of this B, which is not the thing that we want. We want to make sure that this tree is left-leaning. So what is the thing that we should do to fix this? I kind of hear it mumbled a bit, but I think you guys are saying rotate, right? So we're going to rotate this S, right? S was over here. We're going to rotate B to the left, such that this S gets pulled up to the top. B becomes the red node here, so now everything is perfectly fine and we have that left-leaning property that we're looking for. Alright, so the color flip wasn't enough. We'd have to change the right-leaning, or we'd have to change the rotate left that happens right after that to ensure that the tree actually ends up getting into the right position. Okay? Alright, so just as a note, you might be asking, like, how are left-leaning red-black trees even balanced anyway? Like, we do all these random operations, we do all these rotations and whatever. How do we ensure that this actually is a balanced tree? This is kind of an informal proof thing. I wouldn't say it's a proof, but it's just some intuition that I thought of that I think might help you figure out why this actually works. Just remember that I've been saying this through this whole time, that LLRBs have the same structure as their balanced 2-3 tree counterpart. There's that one-to-one correspondence. Right? They have the same exact structure, except for the fact that every 2-3 tree node with 2 items is replaced with 2 nodes in a left-leaning red-black tree. So same structure, except there might be 2 nodes in the place that there is 1 node. And so you can see here there's 2 nodes in that spot. In this spot, there's 2 nodes that represent that one, and then the same goes for this one over here. So the same exact structure, but except there just might be double nodes in some places. And remember that when we talked about this before, the height of the 2-3 tree is going to be log n. We know that the height of an LRB is at most double because sometimes we might have this double node that's occurring right over here. So the height is actually going to be at most double what the 2-3 tree is. So we can see that this height is 2, this one is 4, because the worst case we had these two nodes created this really long stringy side over here. So the height of an LLRB is at most double because every single 2 node in a B tree is translated to 2 separate nodes in an LLRB. Alright? So just remember that because these are always balanced, the LLRBs will also be balanced, so there's at most double that height there. So even though it's double log n, it's still on the order of log n because we can remove those constants. So the LLRB, based on all the rotations that we do, will end up still being in log n height. Alright? So I think this is kind of confusing, but does anyone have any questions about the intuition of why this is balanced? Alright, perfect. So, just as to summarize all the search trees that we've talked about binary search trees, which are simple, but remember that they can become really spindly because we don't really care about the insertion order that we do. We then go into 2-3 trees, which are balanced, but they're actually really hard to implement, especially like the remove method, and they can be slow sometimes. So we will end up going to left-leaning red-black trees or just red-black trees in general because they're simpler to implement. They are BSTs, which is what we're used to doing. So they're simpler to implement and it works because there is the one-to-one correspondence with 2-3 trees. So that's the reason why that it's simple for us and it ends up working because it's pretty balanced. Just as a side note, that Java's tree map, the tree the utils that you can actually use to implement a map is done using a red-black tree, though it's not left-leaning. But you can see that this red-black tree is actually used in the real world where they need to use a tree, they'll end up using a red-black tree because that helps maintain that balance for them. So all those operations are going to be fast. Okay, so just note that this is not all the trees that are out there. There's a lot of self-balancing trees that are out there, such as AVL trees, splay trees, trees, which I think are like a tree and a heap together. So just know that there is a bunch. We just touched the surface of them, but you can go and explore all the different types of trees that you might want to use in any of your other projects or things like that. There are also other efficient ways to implement sets in maps entirely. So we were trying to do set and map using trees. You can actually use these weird things called skip lists. I'm not going to go over what that is, but it's actually really cool data structure that relies on probability, I believe. It's taught in the fall, so you can take a look at those slides over there. Or we can go into a totally different idea, which is hashing, which is going to be next Monday's lab. Hashing is probably the fastest thing ever, so I think it's really cool. So it'll be fun to learn about that. Okay, any last questions about anything related to balanced search trees, left-leaning red-black trees? All right, perfect. So we're going to take a break for now. We'll give you like a 3 or 4 minute break, and then we're going to go into more trees, which is game trees. So take a break, 3 to 4 minutes. We'll come back at like in 3 minutes or so.
Okay, break's over, folks. Let's get back to our seats. Or leave. That's cool too. I'll miss you. Alright. Alright, so I know you've all had a great time talking about trees today. So we're going to keep talking about trees. But what's important is these trees are going to be a little different. So a lot of the trees we've seen so far are trees that will like explicitly store information in them, where you have like nodes, and the nodes have like some value, and you can access the value, and you can see if something's contained, and all of that. But game trees are kind of a different idea. Remember how we were talking about abstract data types and how it's like more of an idea than an actual like piece of information? You know, you can implement a deck multiple ways. A tree is even more broad. A tree is kind of just a general concept where you can use a tree to store data, but you can also use a tree to like think about things in slightly different ways. So we're gonna like touch on that and see if this will make some sense. This is typically one of the like really confusing topics in the fall, which makes it a really good midterm question. So that's cool, right? Okay, so the first thing I want to talk about is this idea of like searching by generating and testing, right? So in the past, with all of our data structures we've had so far, we have some sort of structure and we put some sort of information in it. And if we want to see if something is like contained with it, like if we want to remove something that's inside, or if we want to see if it's contained, like we have our different like operations on our different data structures. Like with a linked list, if we want to see if something's contained, we take our pointer and we scoot along until we find it, and then we report it. And then our like arrays, we like look through the indices and see if it's in there, and our trees will search one way or the other. But the idea is that like we're always searching inside of some sort of set. It might be an ordered set, or it might just be a general set, but we're always searching for an item that exists in some set, and we say, are these items the same? And if they are, let's do something, otherwise let's not. Also, I'm going to turn on the gain because this is, well, all my S's are really, they're too much. All right, is this better? Slightly. Okay, let's do that. Cool. So now, what we're going to do is suppose instead of actually having some explicitly stored data, we have just this idea of like whether something like works or whether something doesn't work. That sounds really vague, and it's supposed to sound kind of vague. But if we don't have some set of information, and we're not looking for a particular item, but we're looking for more of like a scenario or a condition, then we're asking a question that's less of, is something contained within the set? And more of like, is there some item which meets some criteria? So like theoretically, if we want to like do our contains in our linked list, we would be looking for a specific item, and then we would say, once we've reached that item, I'll say like, I'll know if I reached it by saying, are these two things equal? But theoretically, you could also take like your linked list or your array or any other data structure, and you could say, okay, I'm going to look through this data structure until I hit like some number that's even, or I'm going to go until I hit a prime number, or I'm going to go until I find a string that's larger than 5. So there's like, we could be searching for stuff based on like conditions, which is a little different than searching for a specific item, right? But then, like, say I have like a really long list, and say there's multiple items that fit that condition. Like if I have a list of like a bunch of integers, and I'm looking for a number that's even, there may be multiple numbers that are even, right? And so then what if I want like a specific quality of that number that's even? I'm going to have to like look through the ones that have already filled the condition. So what we want to do is this idea of like, okay, we're looking for some characteristic, but then based on the things that we found, I then want to like look through those and decide which ones I actually want. So this is the idea of like generating and testing, where instead of like just saying, oh, this is the one item that I may be looking for, I can enumerate all of the possible items that'll fulfill the category that I'm looking at, like all of the even numbers, and then I can say, okay, based on all of these even numbers, which one is the one that I actually want? So you're kind of generating possibilities for what the answer might be, and then you go into actually testing and seeing which one is what you want. But if you're looking for all the even numbers, and you're looking for all the even numbers that are also like, I don't know, bigger than a certain number or like are factors of another number, theoretically we can like do even less work if we kind of cut out even numbers as we find them. Like if I wanted all even numbers that are, let's see, divisible by like 7 or something, then as I go through and I find even numbers, I can say, well, if 7 doesn't divide it, let's throw it out right now. And then I'll eventually have like a better condition that's like, I'll be able to look for the things that I'm actually looking for. So what's important is that as we generate these numbers and we go to test for them, we can be like clever and doing like some pre-testing as we move through these numbers. But then another question is, what if we have like a bunch of like possible candidates, right? Like what if we're looking for all even numbers divisible by 7, but our list has no n? Like what if we just have a list that has all of the integers? When do we stop and when do we decide when we want to like give up and find something that we want, right? It's kind of a like confusing idea of like, how do you list everything if you don't know where the end of the list is? So using this information, we're going to come to this idea of like, we're only going to start, like when we're looking for something, we're going to like only look as far as we feel comfortable, and we're not going to like try to look to the end because we're going to run out of time and die, because there's only so much time in this world. So here's what we're going to want to do. So has anyone heard of chess? Okay, I got a couple. That's pretty good. So in chess, there's like, how many, okay, when you start a game of chess, does anyone know how many moves there are to start? Like, how many opener moves are there? I have no clue. It's like at least 6, right? So there's a few. But the idea is like, if you want to think about all the moves that there are in chess, like, you know, like I move, and then based on the fact that I've moved, you have like a different like set of moves you can make, right? Like if I move a pawn first off versus if I move a knight first off, your options are completely different. And that's like, I don't know, I guess that's how people win at chess, because they think about those things. I don't really think about those things. But so what this idea is like, if you want to find like the best move for chess, you can't just say like, oh, like I'm going to like just list out all the possible moves I could make in chess, and then I'm going to choose the maximum one. Because there's a lot of things in chess, and there's a lot of moves you can make, and it's going to be like pretty hard to keep track of all the possibilities. So as like a smaller example, like if you want to think about all the moves that are possible, there's this idea that's like the knight's tour, which is like, does everyone know what the knight is in a game of chess? You move in little L's. Yeah, that's the best I've got for how they move. You go like 2 forward and 1 to the side. But what's important is that like they move in a certain way, and what's cool is that you can actually find a way for a knight to visit every single like spot on the chessboard, touching them exactly once, and then coming back to a spot right next to where it would have started. So you'd have like a perfect like cycle if you ran around this board a bunch of times. But it's really hard to find that, right? If I told you to do that, then you'd probably sit there and you'd probably say, okay, I'm going to move this way, and then maybe I'll try this other one, and then it's probably going to take a while to get the exact combination that'll get you to where you want to go. But computers are fast, and we can trust them to do things for us. So what we can do is like, say I have this knight, and I started it at like the 0th spot, and it starts there, and then I'm going to scoot it over to 1, and like this is just me seeing, like I'm going to see if I can visit all the places on the board. And then I'll go to 2, and I'll say that's pretty good. So far I've gotten to 3 spots, and I haven't sat on the same one again, so I'm moving towards my goal. I'll move it over here to 3, to 4, to 5, to 6, to 7, to 8, to 9, to 10, and then when I move into the corner, I think, uh-oh, like now I can't leave as this knight without stepping back on like spot 9 or spot 10, because I've already visited here. And so like all of a sudden, like I had this idea that I was going to be able to visit everywhere on the board, but it didn't work. And so like, who has an idea for what we would do instead to find like how I can visit all the spots? Would we A, just try it again and keep randomly guessing? Or would we B, try to come up with a way to like say, okay, well, the last move I made was from 10 to that spot right there, and I trapped myself. So maybe I shouldn't have moved to 10 in the first place. Maybe I should have stayed here and gone like to the spot above the 1 instead. Yeah? Like if we're not careful, we'll start trapping ourselves. So what we'll do is we'll kind of think back to what we did, and we'll like bit by bit trace back until we find the right answer. Yeah? And like you would trace back and see how far you can get, trace back, see how far you can get. This is called backtracking search, where you kind of like go until you run into an error. So you're generating these possibilities, and then you're testing to see if you've like hit a problem. And then if you hit a problem, then you scoot back until you haven't hit a problem, and then you try it again. And so for us, it would get really boring, but for computers, they love doing this. So we're gonna try to get them to do that for us. Yeah? So does this example kind of make sense of like, you have no idea how to list all the possible moves you can make from a knight, but we want to get to all of them, so we'll like move forward, we'll generate the possibilities, and then if it doesn't work, we'll scoot back. Yeah? Good-ish? Cool. So, oh wait, now I gotta move the knight all the way around. So here's this algorithm that can do it, right? I don't really expect you to read it, but you can if you want. But basically what it's gonna do is it's gonna do this recursive algorithm where it'll have the board, and then they'll know like the position of the knight, and then you basically, as you go through, you mark all the spots that you visited, and then you keep track of like where you've been and where you're going, and then you make this whole path of all the places you've been, and what it does is it tries stuff, and then if stuff doesn't work, then it like recurses back and then tries a whole different path. So it's kind of like sort of like a DFS search where it recurses down, sees until it like hits a bottom state where things go wrong, and then recurses back up and tries it again. So all of a sudden we're hitting this idea that like, all right, this tree structure that we had before isn't just a data structure. It can also model like recursive calls and stuff like that. So it's like more broad than we like initially thought, because a tree isn't just for storing explicit data types. It can be used to store possibilities that we're generating and testing. So here's another kind of search, like best move. Say you're playing a game and there's 2 people in it, right? How many people can win in a game of checkers? Any ideas? Just 1, right? Game of chess, just 1, yeah? So in games like that, your goal is to make the other person lose, which is the same as making you win, right? Those are about the same like value. Like them losing is equivalent to you winning. So if we only have 2 people in our game, then we can try to find like the best move to make, right? So if we're in a game of checkers, you can kind of say like, well, here's one move that would cause me to take all of their pieces and then crown myself I'm the best, and then here's another move that makes me lose. Like, I don't want to do that, right? So you kind of look at it and you say, like, based on where I currently am, I'm thinking about what the board would result in if I take this move, right? And then not only that, you then think, okay, if I take this move and this is what the board looks like, then what are they going to do? And then based on what they're going to do, what am I going to do? And then based on what they're going to do and what I'm going to do, what are they going to do, right? And you start thinking about that way too far in advance, and then you think checkers is hard and you quit, right? But so what we can do is we can use that recursive idea before that we use that like backtracking search from the knight, and we can do something similar, right? So if we want to find like the best move in a 2-person game, theoretically we could like run like a really, really long algorithm, like let's play checkers for a long time, and what we'll do is we'll try every move, and then we'll pretend that the other person tries every move, and then based on them trying every move, then we'll try every move, and we'll just try that until we find the best possible situation. But that'll take a really long time, and it's probably not actually going to be that different moving like the piece in the middle versus the piece next to it, right? So what we'll do is we'll have some sort of like heuristic value, which we'll learn more about later in the course, but for now this is your introduction, where based on the state of the board, you kind of say like, am I winning or am I losing, right? So in a game of checkers, if you have no pieces, you're probably like, not doing so hot, right? But if you have a lot of pieces and they're all like kings and the other person doesn't have many pieces, you're thinking, I'm doing pretty well. So like in a game of checkers, you could say like, okay, to think about how well I'm doing, do I have more pieces than my opponent? That's like a pretty good indicator of how well you're doing, right? Of course, like whether you're like your pieces are like crowned on like the other side and can move backwards. I think that's how checkers works. I don't really know. That has some effect on it. But for the most part, just if I have more pieces than the other person, I'm probably winning. There's something similar in chess where it's not just like the amount of pieces, like since each piece is worth a different amount, like I'd rather have a queen than a pawn. What you'll do is you'll like weight how much each piece is worth and then add them all together and then say, do I have more points than the other person? And that's another idea. Of course, like grand chess masters know that like you should care about positioning, but for most of us, it's just like, hey, I have more stuff than you. Nice. So stuff like that is you can look at a game board and think like, oh, like, am I doing better than the other person? So although like a current state of the game board might say, oh, I'm right now doing better, as we know about like positioning and like the board like that, it could be that you think you're doing well in one moment, like in checkers, like I have so many more pieces, and then the next move, they like jump all of your pieces, and all of a sudden you're down to 1. So stuff like that is why we don't just want to think about the move ahead of us, we want to think further down the line, right? So that's why you did that whole like, oh, what'll they do, what'll I do based on that, what'll they do based on what do I do? So all of that is like, each of your moves you want to think about what your opponent might do. So then if you want to get the idea of like, let's say I'm playing really well, and then let's say my opponent's playing really well, how do I account for that? And then also play well based on the fact that I know my opponent will play well. Well, what we can do is we can use this idea called a game tree, right? So let's say that you're playing some sort of game where there's only ever like 2 options, right? You either move like left or you move right. And then that gives you some amount of points, and then your opponent moves left or you move right, or they move right, and it gives you some amount of points. And at the end, based on some combination of lefts and rights, someone wins. So what we can do is we can think of that whole, like, all those possibilities is we can think of that as a tree, right? So at the top, we're going to say, okay, if I'm like the player, I'm going to think of it from my perspective. The green node is me. I can move left or I can move right. And then based on whether I move left and right, my opponent can then move left or right. And then based on what they do, I'll do something. And all the way down. So this is a situation where basically I get a move, my opponent gets a move, I get a move, and then my opponent like makes some move that ends the game, right? So what this does is this is some sort of like every node in the tree is basically going to be some state of the game, right? And then what we'll do is we'll say we're going to at some point calculate the winner, and then based on like how much the other person has won, I can think about like what moves I want to make. So if the numbers at the bottom are the values of those like final positions and like how they are to me, then like what I'm aiming for is like the biggest positive number that I can accomplish. And so what that means is since it's like my opponent wins if I lose, then my opponent wants the like smallest number, aka like the negative number with the biggest absolute value. So then what I want to do is I want to say like based on this, which direction should I move? Who thinks I should move like right, and who thinks I should move left, and who thinks I have no idea? So who thinks I should move right? Got a couple. Who thinks I should move left? Got a few more. Who's like, I have no idea what this even means. Okay, yeah. So the idea is if I'm the green node and I choose one of these directions, that like cuts off the other half of the possibilities, right? There's no way I can reach them. So like theoretically you might be thinking, well, okay, if I go this way, I might get 15 points, which is really good. And if I go that way, I might get 10 points, which is really bad. Because the maximum I can get over there is 10, and the maximum I can get over here is 15. Obviously, I want 15. Like, that's one way to think about it. But then you have to think about what your opponent might do, right? So then, like, what if I'm just basing off of, well, if I go over here, I might get negative 30, and if I go over here, I might get negative 30. Nothing matters. Who cares what I do, right? Well, let's think about how we can see if my opponent's playing really well and I'm playing really well. Let's try to optimize and get the best score possible. So what we'll do is we'll say, here are my moves, right? These are the ones where I'm trying to maximize my score. And then here are my opponent's moves, and that's where they're trying to minimize my score. And then what I'm going to do is I'm going to like do this thing called a mini-max, right? Where I'm going to take turns minimizing and maximizing at each node so that I can get to like the optimal play for both of us, and then that'll let me decide which way I should go. So since I'm going to think of each like node as a position and each edge is like which move I'm taking, then these like numbers at the bottom are like basically like this game might continue further, but for now I'm just going to pretend that like at each state at this end point I can like count the checkers on the board. I can count the values of the chess pieces and say like 3 moves in advance I'll know what all the possible scores are, and I'm going to base my decision off of that because I can't look much further than that. So then what I'll do is if I'm a maximizing node, I always want to choose the child like to the left or the right with the maximum value, and my opponent always wants to choose the one with the minimum value, right? Because they want my score to be low and I want my score to be high. And theoretically you think, okay, I'm at the top node, which way should I go? Great, there's no values, I don't know what I'm going to do at all, right? So what we'll do is we'll populate the tree from the first point we have values and like populate it back up. So let's start with like, first I have to make some move, and then my opponent makes some move, and then based on my next move, that's when I can start actually thinking of values that I might obtain. So let's just populate the tree back up and see like what my future moves might get me in the terms of value. So based on these nodes here, if I take this -30 and this -5, and those are the scores that my opponent might like generate when they act, would I prefer a -30 or a -5? Since I'm trying to maximize my score, I want -5, right? So then I'll take this node, this maximizing node here, and I'll say like, okay, since I'm trying to maximize my score, and this is what my opponent has to offer me, I probably want to take the thing that's better for me, which is that -5. So then based on these next two nodes over here, who thinks we're going to go with 5? Who thinks we're going to go with 15? All right, cool, making progress. So let's keep filling in the tree, right? So now that I've populated these things, I can keep going and like populating the rest of the possibilities. So like when we have like -20 and -30, we probably want -20, right? And then if we have 9 and 10, we probably want 10, yeah? So we're always choosing the maximum thing now. But so now like I've thought of all the like second moves I can make. So now let's think of what my opponent's move might be over here. So if I have my opponent who's going to move after my first move, they have the option of choosing like either left or right. But we're assuming that we're both going to be playing really, really well. So my opponent knows that if they choose left here, which one am I going to choose? -30 or -5? -5, right? And if they move the other way, am I going to choose 5 or 15? 15, right? So then what'll happen here is my opponent says, well, I'm going to assume that like the other player is intelligent, and they're not going to try to like accidentally minimize their score. And so what they'll do is they'll say, well, should I choose the option that lets them get to -5 or the option that lets them get to 15? What do you think? 15? -5? Yeah, right? So my opponent's going to say, I want to minimize your score. So then same thing on the other side, we'll put in -20, and then when we get to the top, we can say, okay, do I want -5 or -20? -5, right? So then basically what I can do is I can say, based on these possibilities that I foresee in the future, I can think, do I want to go left or do I want to go right? And this wasn't based on, oh, this is the max value I saw, or this is the min value I saw. This is based on both sides taking optimal play strategies, and then what you'll do is you'll say, well, I'm going to optimize based on the fact that my opponent's probably going to optimize. And like, although none of us have made a move yet, I now know that like my best score, assuming my opponent is intelligent, is it occurs when I step to the left, right? Although I could get 10 points on the other side, if I go that way, my opponent should force me to -20. But if I go this way, my opponent can't force me to anything worse than -5. So the worst they could do to me is -5, which is considerably better than -20, and that's why I'll take that choice. Does this make sense so far? Does this not make sense to anyone? And if so, do you have a question that I can answer? Because one question will probably answer many questions. Okay, so based on this situation, let's see if we can quickly get into this idea of pruning. So when we were back here, we saw that like we could just populate the whole tree, right? But earlier in the lecture, slides. We wanted to do, I just want to get to one thing. Okay, we said, okay, we can sometimes be more clever. We want to avoid trying things that won't work, for example. So here's the example. So if I go back to this tree and we go into this idea, this is something called alpha beta pruning, where you don't quite have to know what it is yet, we'll get there. But we can prune the tree and like not look directions where we know that we're not going to like get anything good for us. So what we'll do is we're going to try to do the same thing, except we're going to see if we can ignore any possibilities because they're not going to be very important. So what we'll do is we'll start the same way, and we'll say -30 and -5, I should choose -5, right? So I populate that with -5, and then when we get to this point, we know that my opponent, if they have the choice, they have the choice between -5 and something else, right? So does that mean, like, do you think my opponent will ever choose a value that's greater than -5? Like, if something over here in this like other maximizing node pops up and it's like any larger than -5, will they ever choose it, or will they just default to the smaller value they have? Like theoretically, they'll say, okay, well, I'm just going to default. So what we'll do here is then we'll say, okay, I'm going to hold this idea that I could get -5, and I'm going to hold it in this node for a moment. And then what I'll do is if something better comes along, aka something smaller because I'm the minimizer right now, then I'll update this. And then what we can do is we can cut off possibilities based on this. So we'll go back down to this side here, right? And we'll say, let's look at this value that I want to maximize over. So my possibilities are 5 and 15, right? But when I'm at this like maximizer node, I know that the minimizer isn't going to look for any value that's bigger than -5. So when I see this first value of 5 here, and I see that like, okay, based on the first value that I've seen as a maximizer, I'm only going to keep values that get bigger than it, right? Because I'm a maximizer. What I can do is I can say, I know that I have at least 5, so I'm not going to choose anything less than 5. And I know that the thing above me is going to choose things that are less than -5. I have no reason to look any further because I know that I'm not going to get chosen as a possibility. I know that the minimizer would never go to the right because they always have the option of going to the left, and which is bigger, 5 or -5, right? So what we can do here is we don't even have to consider the idea of that 15 existing. It doesn't matter what the value of that 15 is at all. We don't even have to look at it because we can say there's no way we're going to choose it. So then what we'll do is we'll just ignore it and not do anything with it. And so we've pruned it off the tree. So then in a similar idea, on the other side, we say here's -20, -30, we pick up the -20, and then we come over and we say, well, we know that everything's going to be like less than or equal to -20 because it's a minimizer. The minimizer is not going to choose anything larger than -20. And then we know that at the top, the maximizer can choose either -5 or something that's going to be smaller than -20 or equal to it. So then we can kind of ignore all the nodes to the right, prune those off, and say our end node is -5. We get to the same result, but we have to look through fewer things. So it's probably confusing for now. There is like more code at the bottom that you can look through, but we've run out of time for this lecture, so we'll probably pick this up again on Wednesday. Yeah, what? Next Wednesday. Yes. Yeah, so if you have any questions, you can come to the front and ask. Have a nice day.